move on to the next Monte Carlo event generator tutorial for the EIC. We welcome today Stefan Höche from Femilab, who will introduce the Sherpa Monte Carlo. Stefan has played a key role in that nowadays Monte Carlo event generators are really have a center role or a core role in theoretical and experimental particle physics. And he is known for his work on precision and accuracy in Monte Carlo event generators. For instance, work on running on HPC systems. Sherpa is one of the newest general purpose Monte Carlo event generators. The Sherpa paper has been cited almost 3,000 times, so they're currently at 2,934 citations. Maybe EIC can play a role in getting this up over 3,000. And but before we go there, I'm very grateful that Stefan is today with us and will introduce to us the Sherpa Monte Carlo.
Yeah, good morning, everyone. It's really a pleasure to be here, and thanks for the invitation. I will give a kind of mixed presentation about Sherpa and introduction how to run it, basically. It would probably be a misnomer to call it a real tutorial because I believe that a tutorial should be held in person, and unfortunately that's not really possible right now. But we'll do what we can, so let's jump right in. And I hope that you will learn something about Sherpa. So let me start with the general framework, and I believe that that this slide has been flashed already by Stefan and Simon. It's the general structure of an event generator, and this is the picture that is probably the most used, even if not cited, part that came out of the Sherpa collaboration, originally made by Frank Kraus. And that shows wonderfully how an event is actually simulated. Unfortunately, it's not EP or EA, but it's PP. So you have two protons coming in from the sides here. You have a hard interaction. And for the hard interaction, we calculate the corresponding matrix elements fully automatically at leading order or at next to leading order in QCD or electroweak. Oh, by the way, can you see my cursor when I point to something? Or...
Yes.
Is that visible? Okay, great. So in QCD or electroweak, and of course, like in so many other generators, the actual loop matrix elements, which is the hard part of the calculation, because the other part is done through Catani-Seymour dipole subtraction, actually comes from external programs. Let's say our preferred option is open loops because it's the fastest, and you can also use Recola, you can use GoSam or Black Hat or these are probably the most used that we interface to. But any other program basically that follows the Les Houches standard, or for which we have written a generic interface. MCFM, for example, is one of those for which we have a dedicated interface. And MCFM is great because it's very fast. So then for some very specific processes, which includes deep inelastic scattering in the EP, we have matrix elements implemented in-house, which are next to leading order in QCD. And for the proton-proton part, so for LHC applications, the Z and the W production is done via a slicing method in QT subtraction. We also have Higgs production and diboson production in QT subtraction, and deep inelastic scattering, I will say a little bit about this, is done in the projection to Born method. So you can simulate this at NNLO QCD accuracy. And then this hard process here is calculated using our internal matrix element generators. We have two of those, so you can liken them to MATGRAPH, if you will, except that we don't have the loop part. And it's not as quite as generic as MATGRAPH is, but each of those is essentially a the functionality of MATGraph at leading order and next to leading order subtraction. And these things are called in Magic and Comics, and we learn about them a little bit in this tutorial. So this simulates the hard part of the reaction. This is this big red blob here, and also the decay processes. And the decays, this is an example for PP. So gluon goes to TD bar Higgs. Then the tops that you produce there, if you don't calculate the full final state, will have to decay. And you want to have spin correlations in these decays. And these spin correlations are also simulated fully automatically. The decay matrix elements either 1 to 2 or 1 to 3 decays, as depicted here, for example. So the top goes to BW, and then the W goes, for example, to jets here, or here it goes to lepton. They are calculated fully automatically, and the spin density matrices are calculated and contracted automatically with the hard matrix elements, so that you will get the correct correlations in this factorized picture. And then this is a Higgs decay, and of course you can say that it's also spin correlated, but the Higgs is a scalar, so you don't need to care. Okay, so once you're done with this, you need radiative corrections. For example, the top can radiate both in production and decay. And this is done using either our Catani-Simo based parton shower or the Dyer parton shower. And at each and every point, we can also have QED radiation. For example, the lepton that comes off this W here can radiate a photon, and the photon is this wavy yellow line here. And this is done using the Jenny-Frautschi-Sura QED correction algorithm, which resums soft photon corrections, which are also amended by hard collinear corrections based on Catani-Simo dipole subtraction terms. This YFS, okay, I will say something about that later on. Something that's not relevant for us because we are talking about EP and EA is we have multiple interactions. So the proton is a composite object, therefore you can have multiple scatterings occurring, and this is this purple part here, and we do this in the Sjorstrand-Van Zyl model. After you have produced your hard final state, this stuff has to hadronize all the colorful particles that have been produced here and evolve down to the hadronization scale by means of the parton shower. So the blue stuff is the parton shower, and the light green stuff here is the hadronization. This is done in a cluster hadronization model, but you can also switch to the Lund string hadronization, which we offer as an alternative by means of an interface to Pythia 6. And we can, if you're interested, I can show how this works. Fairly simple, this switching. And eventually, these primordial hadrons or hadron resonances, what's depicted here as the light green.
In a small group, can I ask a question?
Yeah, sure, go ahead. Yeah, and interrupt me at any time, by the way, right?
Is there a significant difference in the result from these two hadronization models?
Yeah, that's a very good question. And the answer is for everything that we've been looking at, no. So I should say, however, okay, I should say two things, and this is something that is currently being discussed in the context of SNOMAS. If you use a Monte Carlo event generator that actually has the same perturbative physics in it, and then you only swap the hadronization model, is there a significant difference, or can you expect a significant difference? And from what we have seen, the answer is no. What people typically do is they run Pythia, they run Herbig, and then they compare, but they compare more than just the fragmentation model, right? You compare two different showers, so two entirely different perturbative models, and then you typically find a big difference. So we have shown in several publications, and maybe I can show a plot later on. I didn't prepare this, unfortunately, but I have some plots that the differences are minuscule if you have the same perturbative physics. Does that answer it?
But I guess these studies have been done only at high energy, right?
That's right. These studies have been done at high energy, and if you're interested in not so much like jet shapes, jet rates, and things like that, then there may very well be a significant difference. So if you look in more detail at the flavor composition of a jet, or single hadron inclusive production, or whatever you name it, then I would expect there to be a bigger difference, because then you're really probing the details of the fragmentation mechanism. But what people typically do at the Hadron Colliders, and to some extent also at LEP, for example, is they actually look at jet properties and then they find differences between cluster and string hadronization, which are truly differences in the showers between Pythia and Herwig, because they cannot just swap out the fragmentation model. And this is one of the reasons why we offer this, because we want to have a more fine-grained look at it. This is why we have two different showers and these two different options for the hadronization model, and why we also have two different matrix element generators. Okay, for the matrix element generators, you know which cross-section to calculate. There is no model dependence, right? You only have randomization, factorization, scale dependence. But at each and every stage of the simulation, we basically want to have the option to do cross-checks and to do systematic studies. And that's why we offer this. I don't know, does that answer it, roughly?
Yes. I just think that hadronization and shower details, hadronization specifically, is something that becomes more important in EIC.
Absolutely.
Yeah, and in particular, what we will find for EIC is that if we are at higher energies for the EIC or higher Q-square for the EIC, then we are really more dependent on the shower. And if we go to lower energies or lower center of mass energies and lower Q-square, then we actually are more sensitive to the hadronization model. To give you one extreme case, if you describe Hermes, having a shower or having not a shower doesn't make any difference, because the energies are so low. So it's the quality of your hadronization model which describes how well it describes things. But then if you then, let's say you go to H1 and SUS kinematics, then of course the quality of your shower and then also the parameters which go in are very relevant in the description of your physics observable.
Yeah. Yeah, and this ties in very nicely with what I said before, right? I mean, you need to know what you're probing. If you're probing the perturbative region, you should really not switch from one generator to another and say that you have different fragmentation models, but then you're probing two different showers. Yeah. Okay, so the point here is that within Sherpa, we offer two different options, both on the perturbative side and two different options on the non-perturbative side, where one is really not a Sherpa option, one is the Pythia option, but there's only a single implementation of the Lund string, so what can we do? We didn't want to re-implement that, but at least you have that option to do the systematics assessment, and we find it very useful. By the way, I should probably advertise this. So I'm also involved in Snowmass QCD, and if you are interested in particular in this topic, that was just brought up, we have this on our radar, and we think it is a very important topic. If you want to submit an LOI to EF 05, 06, or 07, particularly regarding these non-perturbative physics studies, that would be very much appreciated, because we think it will be important going forward. So as the last point, we have the hadron decays. So when these hadron resonances that have been formed in the either cluster hadronization or in the string hadronization then decay, this is implemented also in Sherpa itself through a dedicated decay package, and contains like the 5,000 order of magnitude 5,000 branching ratios from the PDG, and many different form factor models for dedicated decays where it is really important, includes beam mixing and other things. And at each and every point, again, just like in the perturbative part, you can have soft photon radiation, and this is again simulated using the Jenny-Frautschi-Sura algorithm that is attached to these hadron decays. So in the end, you really get the full picture. And everything is in one package. There is no need to attach photos or any other, or tau-Ola or anything. We also have an internal implementation of tau decays with many different models like ISCO-WISE and other things like that. Everything is included. There's no need to attach any external packages, but of course, if you'd like, you can disable our internal tau decays and attach tau-Ola or things like that, right? We just like to have things under control, but we offer options for tinkering with the package, so you can do whatever you want. For example, for LHCb, we offered the option to basically take the generator apart and do the production and the decay of the B individually, because they need this in their framework. And we're always happy to help with that if you have special requirements. Okay, so let's get started with this. I will basically show how this will work, or how you set up Sherpa and how to run it. So first thing we do is we click this link here. Okay, that takes you to the Sherpa homepage. You go to downloads. You take this line here. Okay, and ideally, let's hope that okay, let me close this one. That's the talk. I just created an empty directory here. Okay, can you see this? Is this visible? Is it big enough, the text?
Oh, yeah. Yep.
Okay, great. So sorry, I don't need to create a directory, so I just copy this git clone command. And of course, rel abc is not found upstream. I'll be working with 227, so I replace this by release 227. Okay, so I just do a git clone. So this will download my Sherpa package, and that includes basically all of our releases because it's a Git repository, so you can switch easily from one release to the other. That's also why it's a little bit bigger. It's about 80 megabytes or so. So, well, okay, maybe more like 100 now. So there we go. Checked out. Then you have a directory called Sherpa. Sorry. Then we can do. Sorry. Git status. I always forget. We switched from SVN not too long ago. Okay, so you're now on the release 227 branch basically. And you can do git branch -a or so to list all of them. Okay. Anyway, so if you want to install it, let me go back to the talk. We downloaded this. The latest release is 2.2.10. Okay, so I just checked out the one that we're going to be using in the tutorial. If you want to install, you need your auto tools, automake, autoconf, libtoolize. That's fairly easy to install in pretty much any Linux distribution, and you do autoreconf -fi in this directory. Takes a few seconds. I should say that my laptop is 11 years old, but it's still reasonably fast. So that tells you about how complicated this thing is. Okay, and then you have a configure command with a lot of options. So for this tutorial here, we need hepmc and rivet. So we can just use this command, or we can just ignore whatever I wrote there and say, okay, we just want to go through the configure step. And what you see here is that we have this UPhoto package, which allows you to do beyond standard model simulations, and we have MPI parallelization. This is what Markus mentioned already. We have been quite active in parallelizing our code and trying to run it on high-performance computers. So if you have a machine with lots of cores, or you have a cluster that has MPI enabled, this will be very useful for you, and I will just tell you how to use this in a few slides from now. Okay, so once this thing is configured, just check that everything is okay. You do make -j, whatever, how many cores you have available, and hit install. So that's it. I'm not gonna let it install now. So that was just an example of how to do this. It takes about 5 minutes on 4 cores or so to install this, so it's not too bad. So instead I'm going to create a directory run, which we will use later on. And let's go on. So if you want to test this quickly and play with the generator without having to install it, you can also just go to this page. That is the latest page from the Hadron Collider Physics Summer School this year, but it's actually derived from many tutorials that we have held during MCNet and CTEC schools. And it lists Docker options, and this is what we're going to be using today. To just, pull a container and go through some tutorials that are listed here. All of them are quite useful. This Parton Shower coding tutorial in connection with these TASI lectures is useful to understand of how the generators work. And then this Monte Carlo running tutorial is essentially an introduction to all three Monte Carlos, and it gives you instructions how to pull the containers for all of them. Then there's a Hurwig tutorial, there's a Pythia tutorial, and there is also at some point in the distant future interface here, a Sherpa tutorial. So you can at your leisure go through these tutorials and learn about how to run Sherpa. I will give some very specific EP introduction, so this is for Hadron Colliders here, but it will follow this general outline, basically. So, but you can do this on your own if you like. And there's also a virtual machine option, just in case Docker should not work for you. I have seen many problems with Docker. I have never seen, except once in 7 years, a problem with Oracle VirtualBox, and that problem was actually related to the underlying operating system, which had an issue. So this should definitely work here. So there's a virtual machine disk, and this page tells you how to install it, just if you want to play with the tutorial. Okay, you just follow the instructions on the website, and the links are given in the talk. You can just click on that. It's a hyperlink. Okay. So from there, let me go a little bit through the various physics components of Sherpa. So let's start with the calculation of short distance cross sections in the matrix element generators. As I said before, we have with decent efficiency, or we have decently efficient 3-level matrix element generators that can give us the Born cross sections, and real emission corrections and dipole subtraction terms for the NLO calculations, both in QCD and electroweak theory. One of them is slightly older, that's called a MAGIC, and it works a bit like MATGRAPH. You basically, and we will see this later on in the tutorial, you specify your process, Sherpa writes some dedicated C++ code to disk. You have to compile the code, just like MATGRAPH has to compile the code. Oftentimes nowadays this is done in the background. When you just say launch, MATGRAPH will compile the code for you, and you don't see much of it, but it's still done in the background. And the other one is Comics, which does everything on the fly, and that's a bit newer, and it uses recursive relations and can go to very high multiplicity. Like I said, both of them are MPI parallelized in a kind of trivial fashion because it's a Monte Carlo integration. Of course, the devil is in the details, and you have to pay a lot of attention how this is done, because otherwise you will not get scaling. And I don't want to go into detail here, but we have a fairly good performance at high multiplicity, so you can calculate, for example, in PP collisions, W plus 0 jet processes in about 8 seconds on a single core, and the machine specs are given here at the bottom of the slide. And you can, with less than 1 megabyte of RAM, and you can calculate W plus 6 jets with less than half a gigabyte of RAM on the same machine in 32 days. So the 32 days should be viewed like this. If you have a machine which has 32 cores, you calculate it in 1 day because we have scaling over MPI, right? And if you have a cluster and you can allocate 128 cores to your machine, you get your result in 6 hours. Okay, so that's basically the gist of it. And that is very, very useful when it comes to preparing work packages for the experiments. Atlas, for example, does the integration step, which is really the optimization, or some people call it the warm-up step for Vegas. I believe that's what it's called in MATGRAPH as well. They do this locally on their cluster, which is MPI, which is supports MPI parallelization, and then they ship it off to the worldwide LHC computing grid, where you can't or can only do small scale MPI jobs up to 64 cores or so, depending on the machine that you target. But locally, if you have a big cluster, you just do everything in parallel, and you just cut down the compute time by the number of cores, basically, that you can allocate. So that enables you to have a much, much faster turnaround time. Okay, and of course, the memory consumption is also a big selling point here, basically, because you can do W plus 5jet in less than 100 megabyte, which is quite useful. So then for the next to leading order calculations, we have interfaces to a variety of loop amplitude providers. We offer the Binod-Les-Ouche interface, which is a standard of how to interface the tree level and subtraction generators to the loop amplitude providers. That was drawn up in 2010, or rather in 2009, Les-Ouche, spearheaded by Thomas Binod at the time. And there's an update to this which came out in 2013. We have multi-channel phase-space integrators for both of these generators. They work in very much the same way, except that for comics it's also recursive, and the recursion relation really makes it fast and memory saving. I don't want to go into details here, and we have this Catani-Seymour dipole subtraction both for QCD, which is published here, and then for QED, which was published not too long ago. And for next to leading order calculations, we have QT subtraction, which we did with Stefan Pressler and Jie Li at SLAC a couple of years ago. And for the deep elastic scattering process, we have the projection to Born method. It's not too important how the details of these calculations work. The basic message is that for the standard candles at the LHC and for deep elastic scattering, we have next to leading order calculations available, basically, which can also be matched to parton showers, and I will say something about that in a second. Okay, here's just some performance example. This is a fairly complicated calculation, TD bar plus 3 jets at next to leading order in QCD, which we calculated for the LHC in combination with open loops. That was the first time TD bar plus 3 jets was calculated. And you can see here why this was the case, because if you think only of the glue to TD bar channel, partonic subchannel, then the loop amplitudes that are required for these is for the 0 jet you have 47, for 1 jet you have 630, for 2 jets you have 9,000, and for 3 jets you have 152,000. Okay, and so it goes for the others. The others are very easy in comparison. Basically the TD bar plus 2 jet is a piece of cake nowadays if you use open loops technology, but TD bar plus 3 is still a challenge just because of this very large number of loop amplitudes, which basically means you run out of memory and compute power all at the same time. And here you have a scaling plot of a magic as a function of the number of jets that you attach to the hard process. This is in TD bar production, it's at leading order. So TD bar plus 0, you start here, then you go to TD bar plus 1, 2, and 3. The gray line is a magic, and you can see that the scaling is quite a bit worse than for all other generators. That's because it's an old generator and it uses a not so optimal technology for sorting the diagrams. It's diagrammatic. So there is an inherent factorial scaling in this magic line here. And on the ordinate here, you have the time that it takes in microseconds to calculate a single phase-space point. So if you compare this to MatGraph, for example, the MatGraph is this green line here, then you see that you perform quite a bit worse, about an order of magnitude at TD bar plus 3. TD bar plus 1 is about the same. For TD bar plus 0, you're actually faster. For TD bar plus 2, you're almost an order of magnitude slower. Then if you look at open loops, which can not only calculate loop amplitudes, but also tree amplitudes, you see compared to open loops, you're even much worse, but also MatGraph is worse. So, and that's because the technology that is being used in MatGraph is very much like the technology that is being used in Imagic. It's just they have a better diagram sorting machinery. Okay, but if you use a recursive technique like comics, you're far outperforming all the existing generators for TD bar plus 3 already, and this is where all of them would stop, all of the others, whereas for comics you can go up to TD bar plus 6. Okay, it's just not on the plot because there's not much point in comparing to the others if they can't do it. And the scaling of comics is much better because it's a recursive calculation. So this line is flatter, so you will be able, this is essentially why you're able to do these calculations up to t⁻+6, because the inherent scaling is favorable. Okay, and this is a very well-known thing, and in the computer science community, what we use in comics for the calculation goes under the name of a dynamic programming algorithm. And you're always able to cut down factorial growth using dynamic programming to exponential growth, which is basically what we're doing there. So as far as the next to leading order simulation for deep elastic scattering goes, which is what we are mostly interested in for this tutorial, deep elastic scattering, I'm not going to do NNLO because it's still cumbersome compared to the other leading order and next to leading order, but we'll be trying leading order and next to leading order. Okay, so I stopped one end short of what Sherpa can do. The way this is done is through a dedicated module, because these NNLO calculations are still done mostly as dedicated calculations. There is no generic algorithm nowadays to automate NNLO, as opposed to leading order and next to leading order, which are fully automated already. And this is something that the community is still working on, also being discussed in the context of SNOMAS, the NNLO order. Okay, the way we do this is using a projection to Born method for fully differential fixed order prediction. So there is nothing like a k-factor, so this is all fully differential. And the way we do this is we use matrix elements from that have been calculated by Byrne, Dixon, and Kosovo for the real virtual correction, and also Byrne, Dixon, Kosovo, Berger, and Alm. So this is the Black Hat collaboration back here. And the actual two-loop matrix elements are extracted from these original papers by Willy van Nerven and Sven Moch, which are listed here. And they are put into the code in a dedicated fashion. And then all of this is matched to the parton shower using the An-two-loops technique that we devised together with Stefan Stefan wrote it down from the theory perspective together with Leif in 2012 in an appendix of this paper, but then the first time it was actually done in practice was in this collaboration at SLAC in 2014. So in order to make this viable for both jet production and inclusive deep elastic scattering, we have to choose a scale that reflects the actual kinematics of the process. And if you look at deep elastic scattering, for the inclusive case, what you have is a virtual photon that scatters off a quark, and the quark backscatters, so the usual thing in the bright frame, basically. And there's a single kinematic quantity that, well, two kinematic quantities that you can write down. One is the Bjorkian X, and the other one is Q squared, so the virtuality of the photon. And of course, yeah, you know all this. I just want to mention that when you go to next to leading order, there are more kinematic quantities. There's Q squared, there's X, and the dominant process at high transverse energies of the quark is actually not the original deep elastic scattering process with some quantum corrections to it, but it's something that I would consider a different partonic channel, and that's universally viewed that way, I believe. So when the transverse energy of that parton or jet here is larger than Q squared, you have kind of a situation where this blob here is harder than the incoming photon. So this is the hard process, and the hard process is QCD Compton, basically. So you have kind of a transition from deep elastic scattering, or actual deep elastic scattering, to something that looks more like photoproduction when you attach even more particles here. And this has to be reflected by the scale choice in order to do a decent job with the actual NNLO calculation. And there was a paper by the NNLO JET collaboration, also in collaboration with experimentalists from DESY, Daniel Britzker and others. The NNLO JET collaboration is Nigel Glover, Thomas Gehrmann, and others, Alex Huss and others. And they came up with this scale choice here, which is leading on another scale choice that was derived by the Black Hat collaboration in the context of W plus multijet simulations. And it essentially smoothly interpolates between Q squared for this type of process and the total visible transverse energy in the bright frame in this type of process. So it chooses whatever is greater, basically, as a factorization and randomization scale, and that gives a fairly good description of the higher order dynamics in QCD. So we can look at what this would look like in comparison to experimental data, and this is taken from our paper in comparison to H1 data from the Hera collider at DESY. These are run 2 data. This is for inclusive jet production, this is for dijet production, and this is for trijet production, and you can see the prediction at fixed order, which is the green one, which for this type of calculation is really a next to leading order prediction, because you have inclusive DIS at NNLO, but this is the inclusive jet, dijet, and trijet selection, so there the predictions are only next to leading order for the left two, and for the right one it's actually leading order, because you have to require 3 jets. So that's why it's labeled NLO here. Okay, and you can see that the uncertainty bands are fairly small. These are perturbative uncertainty bands, which are given by varying randomization and factorization scale. And then, so the fixed order predictions in green and the matched, Parton-Shauer matched predictions in red, which have fairly similar uncertainty bands. They agree also very well with the fixed order predictions, and they also agree very well with data. If you look at the original publication, you will have ratio plots where you can see that within the uncertainties, this agrees very well. So the reason why we calculated this is not because it's so great to simulate NNLO in Chopper. In fact, it's pretty terrible because the efficiency at NNLO is disastrous. But because we wanted to extract the hadronization corrections that are required in order to compare these data to the N3LO calculation by Thomas Germann and his collaborators, because the hadronization corrections which were extracted by the experiments involve a Monte Carlo that is not based on collinear factorization. And then, of course, you have to ask yourself, how much, or do these hadronization corrections mean anything? Because if I have a different underlying perturbative physics calculation, is it actually sensible to extract these hadronization corrections and then use them for collinear factorization? No, it is probably not, because I have different underlying perturbative physics. So how can I assume that my hadronization corrections are the same? So here the hadronization corrections, and they are in the paper, are extracted based on D-club-based Parton-Shauer and Monte Carlo, and they still agree fairly well with the other Monte Carlo, which was based on the dipole model, but that wasn't clear a priori, and we wanted to clarify this. The interesting thing is that this calculation does not only work in the high Q-squared region, which is somewhat expected because you have, thinking of the kinematics again, a typically DIS type situation. Q-squared is high, so you can go to high transverse energies of the jet, and you will still not end up in this situation where you have the reversed scale hierarchy. But it also works in a situation where Q-squared is very low and where you are actually very close to the photoproduction regime. So Q-squared of order 5 GeV squared or 8 GeV squared, so Q is order 2 to 3 basically. Even there you have a very good description of even the trijet region in comparison to experimental data. And for the dijet selection you're basically spot on. And the reason for that is because you actually simulate the BFKL type of effects that you can have in this situation with the explicit full higher order calculation. Okay, and that is sufficient to cover the kinematic range of Hera. And this is all explained in detail in the paper and in a previous publication that we referred to. How this interplays with BFKL effects. Okay, are there any questions on this so far? If there are any questions, feel free to speak up, right, at every point. Somebody opened the microphone, or?
No, I just wanted to say a comment. No questions from my end. So.
Okay.
Just to give you some feedback. I think it's clear and
Okay.
the precision is clear.
Okay. So then let's go on to, I want to flash just to show the capabilities of the generator a little bit, what we can do in context of BSM simulations. Because EIC will probe standard model at high precision, maybe there's also a need to simulate specific BSM scenarios. We can interface to UFO, or we have the UFO standard in the generator, so you can use fine rules to generate from your favorite Lagrangian a UFO file and then plug this UFO file into Sherpa. And there are some glitches with it at times when it comes to form factors. Not everything is implemented yet, but we are working on this. Currently, we only support spin 0, 1/2, and 1 particles. If you are interested in Rarita Schwinger or gravitons, contact me. I'm the responsible for this kind of interface because it basically involves comics and defining new external wave functions in comics. We haven't found the need yet to do any other spins, but we certainly can. It's not a problem. This thing was tested for a large set of processes against a dedicated paper by Kaoru, Tillman, and collaborators, and against benchmark scenarios that were given in this original fine rules paper here. And we found for a large number of processes, so 60 in the standard model, 13 in the Higgs EFT, 401 in the MSSM, which came from here, 51 in minimal UED, and then 16 for anomalous quartic gauge couplings. We found perfect agreement basically with MATGRAPH. So this is the maximum relative deviation for 1,000 phase space points that we found for 1,000 random phase space points in comparison to MATGRAPH, and you see that they all agree. Okay, so this is just the summary table. And the last point here is interesting because we can do anomalous gauge couplings with this, so you can also do generic EFTs basically, and this is being explored at the moment with the help of Sherpa as well in Durham. So we are extending our capabilities there. There are there are always a couple of bug fixes to do, but it's not a big deal, and not more than in any other generator. The capabilities are there, and you can go to arbitrary higher dimensional operators. So this anomalous quartic gauge coupling test here involved up to 8-point vertices, for example, to do these calculations. So it was very interesting. This is just an example for the spin correlation algorithms. So you have here on the left PP to DD bar to BB bar, electron muon to neutrinos, and you're testing the delta phi between the electron and the muon. And if you don't have correlations, you get the blue line. If you have spin correlations, you can calculate this with a full matrix element in Sherpa. So you just specify the full final state, no problem with that. You get the black line, or you do it with the factorized production times decay matrix element. And then if you have spin correlations, you would expect the same structure. And that's also the case. And we test here that the relative deviation between the red line and the black line is only statistical. So this is normalized to the individual uncertainties, to the mean of the individual uncertainties, and then you find this is a fluctuation around 0, which fluctuates at most 1 sigma level as expected. The same here for supersymmetry scenario, PP to ups quarks and decays to neutralinos. With down, up, and a muon and an electron, and again you're testing some correlation between the up quark and the positron. Again this agrees at the statistical level. So this is all validated basically. Okay, and then what's quite important in the context of these calculations is that you can do uncertainty estimates. So you can either do explicit variations, of course, you can do that in any generator. You can vary your randomization factorization scale and run it again, which is not so convenient because you will have to run it again, and the events that you get may not be correlated with the actual events that you produced beforehand. Advantage is that you can change the functional form of the scale to anything you like. But we also offer, like many other generators do, or most of the generators do nowadays, on-the-fly variations. So you can do this for the randomization and factorization scale, for pattern distribution functions, and for showers. I will show the shower variations later on. And in this context, you can at the moment not change the functional form of the scale. So if you stuck, for example, to this mean of q squared and ht that I showed before, you will have to stick with this. But in principle, we can extend this if it's needed. It's not a problem. And the syntax is given here, so it's fairly simple. You just specify scale variations, and then you list your favorite choice of parameters. So the first one is always randomization scale factor. Factorization scale factor is the second. So this is a pair of randomization, factorization scale choices, and then this is another one. So this would be, all the scales are squared in Sherpa, so this would be a variation by a factor 2 down in both mu r and mu f, and this would be a variation by a factor 2 up. And I will have this as an example later. And these variations are stored in the HepMC weight container. If you analyze with Rivet through our direct interface, you will get this. You will get the output automatically for all the variations which are labeled correctly.
Stefan, may I ask a question?
Sure, go ahead.
And it might be the wrong slide to ask these questions. So you list here parameters where you know what the uncertainty is. So for PDF, it comes with an uncertainty.
Yes.
But I've also have tuning parameters in the in Sherpa.
Good question.
How do you handle, or would you come back to this at a later moment? How would you then handle uncertainties in these tuning parameters, where sometimes one might not even exactly know what is a good estimate for them?
Yeah, so that's a very good question. At the moment, we don't have the capability to do these variations on the fly. This has to do with the fact that many tuning parameters will affect the actual outcome of the simulation. So if you change the fragmentation parameters, you will change the decomposition of the hadron spectrum that you get at the end, or you will change the multiplicity. When we do variations, we only do variations that don't affect the kinematic distribution of the final state, but only its weight. So you can imagine that if you change, like what I said, right? If you change flavor parameters in the hadronization, of course you can assign a weight to that, but this is not implemented yet. Okay, let me get back to the question in the context of showers later. And in the context of fragmentation, the answer is we don't support this at the moment. It's something that we may want to think about, but I would have to discuss this with our hadronization expert, who is Frank Kraus. For showers, we support the randomization and factorization scale variations that are listed here. We don't currently allow variations of the kinematic scheme in the shower, because it is also very difficult to calculate the related Jacobians. So if it's really what we typically consider tuning parameters in the Monte Carlo, the answer is that there's no such facility. It's essentially the parameters of the perturbative calculation that you can vary, and the parameters of the matching and merging. Does that answer it?
Yes, and I'm also aware that the question which I raised is generic to all generators, and I think is something which is very difficult to do.
Yeah, I think the answer is probably also universally the same, at least as far as I know. It is something that we may also want to pick up in the context of Les Houches. At least this has, Les Houches and SNOMAS. So this has been brought up already, and clearly it's an important point as we go forward and computing resources are getting scarce. Okay, so this is just an example for one of these on-the-fly variations. So in green, you have a band for the randomization factorization scale variations. And then in yellow, you have essentially a closure test. The green is an explicit variation, and the yellow is the on-the-fly variation. And in this paper, a lot of closure tests were performed for the PDF uncertainty, for the mu R, mu F uncertainty. So this comes from the variations in the NNPDF set, so the scan over the different Monte Carlo replicas of NNPDF. And then this here comes from the mu R, mu F uncertainty. And you see that the closure test works basically. Okay, so with this, let's go to our first actual exercise. And I just want to show you that it's not very complicated to set up a Sherpa run card. And we'll start from scratch basically. So let me start from scratch and let me quickly explain what we are doing. So we first create a file, which for the existing versions of Sherpa is called run.dat. In newer versions, we will change this to a YAML format, but the basic names of the parameters will all stay the same. So I like to work with screen. So let me just open a screen here. I'm also an Emacs person, so let me open an Emacs. Okay. And then I'll just do drag and drop, and I'll start with this run section here. Okay, so this is a section that specifies the generic parameters for the run of Sherpa. We first set up the first beam at 26.7 GeV energy, and this beam is a positron. So we're trying to target Hera there, Hera 1-1. The second beam is a proton, and it has 820 GeV of energy. What you can also see here is that when you write this run card for Sherpa, you can write things on the same line as long as you separate them with a semicolon. Okay. You don't need the semicolon at the end of the line. You may put it there, but it doesn't hurt not to have it. Then for deep elastic scattering, we need this flag here, which has to do with the beam remnant simulation, and it essentially says, okay, whenever you have a massless quark, keep it massless, because what we do is we do a slight trick in the transition from the hard matrix element to the parton shower, because it's not necessary to consider the bottom quark mass at the LHC, for example. We calculate with massless bottom quarks at matrix element level, but then make them massive in the parton shower stage. That saves a lot of memory and computing time, because you can then map the matrix element for bottom quark production in many processes that don't involve tops to the matrix elements for down quark production. So it's essentially just a time saver. And to disable this, you have to put this flag, because we don't want to automatically make this transition to massive bottom quarks, because that screws up our beam remnant simulation in deep elastic scattering. Because DIS at Hera is much more sensitive to the actual dynamics of the hard process, because you're at lower energy than LHC. But our default is LHC, so... Sorry, go ahead.
I must have missed something. How do I do this inside the Docker container?
I'll get to this in a second. File? Okay?
Okay.
Yeah. I'll get to this in a second. So just open... Okay, if you want to follow along. So I just created a directory here, okay, anywhere on your machine. And I just created this run.dat. Sorry, I haven't saved it yet. I just created this run.dat in this directory. Okay, so you just have a local folder, and we'll work on that local folder with the Docker container later. That makes it a little bit more convenient, because you can use your favorite editor to edit the file, and also your favorite browser later on to display the plots. That's why I like the container. The container is really just for running Sherpa.
Yep, I got you. Thanks.
Okay. So we also, just for the convenience of this tutorial, because it makes the calculation slightly faster when we go to next to leading order, disable the electron PDF. And you can do this by specifying PDF set 1 none. So the 1 refers to the beam 1, okay, which was the positron. And we just disable this PDF. You can also keep it on, but for the example we are going to have later on for the one-jet process, it makes it slightly faster to turn it off. And I just want to get through it in time. Okay, and then we have to define a scale. Shopper allows you to define scales in very arbitrary forms. You can write your own scale choice, and you can link this to Shopper on the fly as a library. But we also have this variable scale setter here, which inside these parentheses allows you to write an algebraic expression that involves the momenta of the hard process, and we start counting at 0. So this is the incoming positron, basically. And this is the outgoing positron, because the notation will be like basically minus 11, and then something goes to minus 11 something. Okay, and you will see this later. So when I pick out number 2, I pick out this particle. So I take the momentum of the outgoing positron, of the incoming positron, I subtract the momentum of the outgoing positron. I take the abs squared value of this, so the square of this difference of 4 momenta, which is q squared, and because this is a negative number, I put a minus sign in front of it, and that gives me my scale definition. Okay, my scale definition is q squared, basically. So this is q squared equals minus q squared. Okay, and you can comment, as you see here, with a hash mark. Okay, so next thing is we have to set up the process. So I copy this thing, I dump it in here. Okay, now you see what I just said before. So now you set up the hard process, which is positron, and then this 93. 93 is a container for light partons. Okay. So you scatter positron, light parton to positron light parton, basically. Okay, and Shopper will make sure that there is a proper transition from this proton here to the light parton by means of the PDF. If you don't specify a PDF, it will be the default PDF set, which is NNPDF3 at the moment. Okay, and then we also need to make sure that the cross-section is regular, which means you need to put this cut here, which we call a selector. Okay, so the selector is, okay, we have a q squared selection that acts on the positron, and our q squared ranges between 4 and anything, basically, right? Because we don't want to have an upper bound, so I just put an arbitrary number. Okay, and this is it. So with this, we go to the other terminal, and now comes the Docker container. Okay. All right, let me briefly flip back to my, let me see, to my other page here. So I do what was stated on this page, which is also the one that is listed for, sorry, I stripped that down a little bit. So this container installation page for this tutorial is given here. So I do docker pull, and this will take a while. So I've done it before because it's about 1.7 or so gigabyte container, because I installed Rivet and a lot of other stuff that we're going to be needing. So, and then you can say Docker images, and you have this here, the CTech School tutorial. Okay, so that's the size of the container. Okay, and then I copy this alias here because it makes running a little bit easier. I dump this here. So that basically says, if you don't know Docker that well, that I run an interactive container, I map my user ID, I mount my home directory, and I mount my working directory, and I set an environment variable which is called Rivet analysis path, because we're going to be using Rivet later on. Okay, and now I can go, okay, I have the run card that I wrote here in this directory. Okay, now I can say docker run shopper. Okay, and shopper is installed, so you can just do a tab complete here. Shopper will always pick up a file that's called run.dat, at least in version 2.x. Okay, so you can run Sherpa. I don't want any events for the moment, so I type -E0. So no events for now, as it says here. And I just run it. And what it will do is, let me just stop this for a second. It will set up the process, which is a 2-to-2 process, positron J, as we call it. And this J stands for jet. And you can find further upstream what the definition of this jet is. There's here list of particle containers. Jet has the KF code 93, which is a free code. So we define this to our liking, and this is the 93 I gave in the run card. And it contains the down bar, up bar, SS bar, CC bar, and BB bar, and the gluon. So anything that's a light parton, okay? And whether or not it's light, you can tell from the massive flag here. Okay, so even though the particle has a mass in principle, and this is what I said about the bottom quark earlier, it's not switched massive, and that means it's contained in this light flavor container, okay? As opposed to the top, for example, which has a mass and also is switched massive, so it's not contained in this light flavor container. If I go to a 100 TeV collider, I would say massive 6, basically like this, massive 6 equals 0, then the top would not be massive anymore and it would be contained in this light flavor container. Likewise, if you want to do a 4 flavor calculation, you can say massive 5 equals 0 and the bottom quark will not be massive. Okay, so this is how this is determined. All right, so that's how we set up this process. So it's E plus jet goes to E plus jet. It's calculated with comics. That's the memory consumption of the entire executable, so that includes the process, which is virtually 0, and then all the rest, basically. And then Sherpa says, okay, I'm starting the calculation, and this is really what's called the grid warm-up in other generators. So you can see during this grid warm-up what the cross-section looks like and how the uncertainty, the Monte Carlo uncertainty is developing, and what the phase-space cut efficiency is, and how long the calculation will take, and when it's going to be complete. Okay, so let me continue this. It only takes a few seconds. So that was step 1. Then you may want to be, then you may be interested in what kind of Feynman graphs contribute to your calculation. So let's do this. Let's write out the Feynman graphs. So I say print graphs. Sorry, it never copies the underscore. Okay, so let's do this again. You will immediately see that Sherpa will pick up the integration grid that it created before, and so it will not recalculate, but it will just pick up the result from above, okay, and give you the efficiency for the integration. And that's because there is this file results.db, which is a SQLite database where all the results are stored. Okay, so if you want to recalculate something or force Sherpa to recalculate, you would remove this results database. And then it just created this directory graphs here. Okay, and I can plot, there's a script that comes with Sherpa that does this. I can plot the Feynman diagrams that are in there by means of LaTeX and FeynMF with this command. Okay, and then I can view this with my favorite browser. Okay, and you can see here the Feynman diagrams, or you can download them if it's a bigger set as a PDF, and it will label the particles in the order that they were produced in Sherpa. So 0 and 1 are the 2 beams, and then 2 and 3 are the outgoing particles, and you see that this is a T channel. 0 and 1 are connected by means of this photon here, and here they are connected by means of this Z. Okay, so if you use your favorite BSM model, or the other graphs that you would expect would appear here at some point. Okay, so that's how you get the Feynman diagrams. And that concludes the leading order part of this thing. Any questions so far?
Just hold 1 minute. I'm trying to work along, and I just want to open this in my browser right now. I think I've got it all, but let's see.
Mm-hmm. You got to
Very
pay
nice.
attention.
Yeah, that works.
Okay, perfect. You got to pay attention if you copy these statements here from the talk, then for everything that's not in this verbatim environment, the underscore doesn't work.
Yeah,
I,
I
I
just
couldn't figure
noticed
out
that
how to
too.
make that work. Sorry about that. Okay, great. So then, okay, sorry, this is this slide is labeled the wrong way. Of course, we're not doing PP. So now we do the calculation at next to leading order. Okay, and this is basically just to show you that this is really a piece of cake if you have the matrix elements. So let's remove this print graphs. We don't need that for the moment. So instead we put NLO QCD mode fixed order. So we do a fixed order calculation first before we match it to the Parton shower. And we say loop generator open loops. Okay. Simply because open loops has a large set of matrix elements available. Okay. So now when you, however, it is not particularly fast for the 2-to-2 processes, so you will find that there's quite a bit of a slowdown, but it's really the loop matrix elements that take so long, okay? So if you start the calculation, you will see now, okay, you are using one loop, and this is for the integral library. You are possibly using Collier, which is for the integral library, and you're using, like here, open loops too, okay? Okay, so you're calculating and you find, okay, this becomes quite a bit slower. We also have an internal implementation of these matrix elements, and they are much faster, and we get back to this later on, but they won't work with comics because we usually don't care about using comics when we do NLO calculations, at least not the loop part. We do this more for the trees. So, since this is a bit slow, I interrupt it, and I'm going to show you how to do this with MPI. So you can use MPI run -N2, for example, if you have enough cores on your system, and it will get a bit faster, basically. Okay. However, we don't need this. Oh, actually, we do need it. Right. I want to show you something. Okay. So let's integrate a bit longer until we reach about 1% precision, which is usually the threshold for Sherpa to say, okay, that's enough. I'm going to stop there. Okay, so this should be fine. Okay, so now I want to show you how to generate events in HepMC output format. So I take this line, and this line, because of this -E10K, you could also write 10,000, will generate 10,000 events. Before we had -E0, so we specified no events, and the default is 100, so I just want to change this. And this -w means I want to use a weighting strategy, and this weighting strategy shortcut is W is for weighted, okay? U would be for unweighted. Unweighted events at fixed order QCD don't make sense, so we use weighted events, and we output them in HepMC format, HepMC short format. Okay, and we write them to a file that is called events. Okay, so let's do this. Oh, yeah, and I forgot that we also have to integrate the real emission correction. So now you can see here that there is a born, virtual, and integrated part of the calculation. Okay, and what's being calculated now is the real correction. Okay, and I stopped short of finishing the optimization on this, which is why the efficiency here is pretty low. Okay, we can maybe wait for 1 minute here until it finishes the real emission calculation, and then we just generate some events.
I'm ahead of you, because I could use MPI run 6.
Ah, too bad. My machine is too old. Okay, so if that's working well for you, that's great. Okay, just in the interest of time, I say okay. I accept that there's an uncertainty that's slightly larger. I just reset the uncertainty to 2% and I generate some events. Okay, so now you see how this works. what's quite important to realize here, let me go back to this before I explain the event generation. When you calculate the real emission correction and all is working well, then quite often the real emission correction is very much smaller than the Born virtual and integrated subtraction part. That's because it's an NIO calculation, and if it's set up nicely and kind of all makes sense, then that's what we would expect. Therefore, the relative uncertainty that is given here is not so meaningful, but what you should consider is really the total uncertainty in comparison to this number. So stopping short here at 2% relative uncertainty makes total sense, because that is actually already less than half of the 1% uncertainty that we have on this number, if that makes sense. Okay, so this is why it's totally fine for me to stop there. Okay, so now Sherpa told you, okay, I am generating events with a perturbative phase that's called signal processes, where the cross-section really comes from comics, which we have up here. We have hard decays, which are inactive. We, in principle, have a jet evolution that is inactive. Everything else is inactive, and we have an analysis output that is HepMC, which is really just writing to event files. And you can have a look at this. I said the event file is called events.hepmc. And that's a zipped file in this particular case, where we installed Sherpa on this container because it's installed with zip library support. And you see your standard HepMC output, basically. Okay. I never know how to read this right, but what I do know is that here are the particles, and that's your incoming positron, incoming quark, and in this case it was an up quark, outgoing positron, outgoing up quark. Okay.
Can it do HepMC3 as well?
Yes, we can.
All right.
So now we want to try what happens when we do scale variations. When you have scale on-the-fly scale variations, again, there's the problem with the underscore. You do exactly the same thing, and Sherpa is warning you because it says variations cannot be written to HepMC without using named weights. So I'm using named weights, putting this as an extra command line option here. You can always put this stuff directly on the command line or in the run section of the run card. Okay, so I'm writing these, and I'm doing less on that file. And now you see that there is this name line here, and then we follow the Lesouche standard. So there is a down variation by a factor of 2, and here the scales are not squared. Reminder, here in Sherpa the scales are squared, so it's 1/4, and in the output it's not squared, so it's 1/2. And this is the up variation. Mu r goes up by a factor 2, mu f goes up by a factor 2, and this is that's basically this thing. Okay, and then there's the PDF label too, and you can do PDF variations too. Okay, so that's basically how it works if you want HepMC files. Any questions so far? If not, then let's just move along. So the parton showers that we have are, as I said, the parton shower based on Catani-Seymour dipole factorization or Dyer. In both cases, we solve the soft double counting problem by matching the soft iconal term onto collinear terms by means of partial fractioning. So this is the standard Catani-Seymour trick. Yeah, as I said, 2 implementations of this. One is what we call the CSS, Catani-Seymour shower, for lack of a better name. It's a collinear parton shower, which is transverse momentum ordered, and it has pure Catani-Seymour dipoles. And we have Dyer, which is very similar, except that it's dipole KT ordered, and it has slightly modified Catani-Seymour dipoles. Essentially, we use this partial fractioning strategy here and then rewrite it, the matrix element in slightly more convenient form to have something that looks like a standard dGlub kernel here. Stefan will probably have explained this in tutorial. So this is in his tutorial. This is also implemented in Pythia, which means that you can very carefully cross-check your Monte Carlo predictions between Sherpa and Pythia, which should come in very handy if you do validation in the experiment. Also in the Parton shower, you can do uncertainty estimates. So this is an example for the uncertainty estimates. Again, you can run mu-f and mu-r up and down by a factor of 2. You can do PDF variations, which is this CT14 here. This is just an example for the PT of the W and the closure tests, just like what I had before for the PDF uncertainty and the mu-r, mu-f uncertainty. For the PDF uncertainty, the closure test is only on a statistical basis because it will change the behavior of the Parton shower. Because when you change scales in the Parton in the Parton distribution, you may run into a situation where the Parton distribution actually becomes 0, and that is very difficult to reweight if you reach this step in an intermediate branching or rejection. Because then you cannot divide by the 0 for the weighting algorithm. So this is has to some extent statistical fluctuations which come from this effect. Okay, so let's go to a Parton shower simulation. First thing we're going to do is we remove the NLO QCD mode fixed order. We will start with a Parton shower, not with an NLO match calculation. So let me also remove the scale variations for now. So we remove the NLO mode fixed order and the loop generator here. Okay, so that means we are now going back to leading order. I remove all the other stuff here. We don't want event output anymore, and we want to generate unweighted events, so I remove the weighting strategy. So for this tutorial, I had to slightly hack Rivet because we have the funny feature in Sherpa, and it's interesting that I didn't realize this before, but okay, the routine that I'm going to use here, the H1 analysis of the transverse energy flow, which was probably also used by Simon, is also contained in HZ-Tool. And we have a dedicated HZ-Tool interface in Sherpa, so you can run HZ-Tool analysis with Sherpa directly. Okay, and this is why we didn't realize that there was an actual issue, because this Rivet analysis here is configured such that you have to use the positron on the second beam. But Sherpa is configured such that the positron is always on the first beam. So this is something I'm going to fix, okay? But I couldn't fix it for this tutorial because I wanted to use the old container to show you that in principle all of this comes out of the box and I don't have to do anything. Unfortunately though, because of this, the only thing that I have to do is recompile this analysis. So I hacked this slightly to swap the beams around, okay? But that's all. So let's do this. I get this hacked analysis from my webpage. I untar it in the same directory that we're running, and I build a local Rivet analysis, which is really exactly the same as this H1 analysis, that's why I just put this underscore here, except that the beams are swapped around, so it matches the Sherpa convention. Okay. So after you've done this, you will have this Rivet analysis.so. So you will have seen this in the Rivet tutorial, how to build a local analysis. And then I'm just running with this, okay? But after...
Can I pause you for a sec? Could I share my screen? Because I get a problem with that.
Okay, let me stop sharing and you can share.
I'm running from directly inside the container. And
okay.
Can you see this? And here is where I'm trying to build. So I got. Oh, yeah, and here I'm trying to build the plugin.
Yes.
And this is what happens.
Oh, you have this MCDIS mod, which is probably the one that you have from the previous days, right?
Ah.
And this is for a different Rivet version. So what we have installed here is 2.7. And I guess you have version 3. So you should really only compile the file that starts with H1. And I mean, you can still do the Rivet build plugin, but instead of the star.cc, just do h1 star.cc. And that should do the trick. Or this, yes.
Yep, that did
Okay,
it. Thank
perfect.
you.
Okay. Yeah, I mean, sorry about that. I mean, what I should really do is fix this issue in Chopper, but I just didn't manage to get it, or
No,
rather didn't
it's
want
my fault
to
for
do it
reusing an
for.
existing directory right now.
Yeah, I mean, if I had taken the H1 analysis from version 3, it should all work, right? I mean, it would compile everything into the same directory. Okay, so then after you do this, you can run Chopper with this command. So what we're doing now is we generate 10,000 unweighted events, and we use the Rivet plugin for analysis. Okay. So it takes a bit longer to start up now because it initializes the fragmentation and decay, and it generates events. So you can see here that the analysis plugin being used is Rivet. And after the 10,000 events are simulated, and that's the total cross-section that you got from these 10,000 events, I'll get back to this later, you will have a file here which is called analysis.yoda, which is the output from Rivet, so that's the Yoda file, and then you can do rivet-make HTML analysis.yoda. Takes a while because it fires up LaTeX and all sorts of things. Or maybe my machine is just slow. Okay, whoops. Why is this not working? Oh, because I haven't put the analysis in yet. Oh, I'm an idiot. Okay, sorry about that. So I have to do this again. I have to dump this in here. Okay, this -a specifies very much like the command line option for Rivet that you want to enable a particular analysis. Okay, and now it's also being used. And afterwards we can make the plot. Yeah, sorry about that. But fortunately these things don't take too long. Okay, and now we can do a Rivet make HTML. Yeah, and as you can see here, it's fairly easy to specify an analysis. You can have multiple blocks here, and for each of these blocks you can specify also what the name of the output file should be. And you can also specify internal analyses with Sherpa. So there is, or you could do begin HZ tool, for example, and if you have HZ tool enabled, then you can do HZ tool analysis or whatever, if you're interested in Hera physics. Okay, and then you would specify the analysis. There's an example in the Sherpa folder which tells you how to use HZ tool. Okay, so now we made some plots, and let me bring them up. Firefox, Rivet plots, index HTML. Okay, now we have this H1 analysis, and it doesn't look too good, but we're going to work on that in a minute, and you get your comparison to experimental data. Okay. Okay, so now let's try to improve that prediction a little bit by going to next to leading order. So I'm going to the next slide. Now we're going to do MC at NLO matching. Okay, so for this we copy these lines and we dump them into this process definition. To make the calculation of the real emission matrix element a bit faster, we use comics. In order to make the virtual calculation a bit faster, we use a magic and our internal loop matrix element generator, which for DIS is really just trivially the 8CF that you know from textbooks, basically. And we say we want to match this using MC at NLO techniques to the parton shower. Okay, so that's all. Now we do matching. Again, we run Sherpa. Okay. And because we use a magic, I said before that a magic writes code, we see that Sherpa stops here at some point, but it's a normal exit, so don't be puzzled by this. And it says here what you should do. It created source code, and you should compile this source code using this command /makelibs. So let's do /makelibs. If you want to have it a bit faster, you can do -J6, -J2, whatever, how many cores you have. It should still be fairly quick because it's a very simple process. All right, there we go. And now we can run it. It will again calculate a cross section, and you can see here already that it's about factor 5 faster than what we had previously with open loops, and that's simply because the loop matrix element, if you implement it analytically, is much faster, right? The strength of open loops is really at higher multiplicity, where you don't have analytic matrix elements, and you need to use the open loops or OPP technique to calculate your matrix elements on the fly. Okay, komm mal kurz her, Julia. I'm sorry, give me just a second. My daughter just came in. Okay, sorry about that. Okay, so let me share again. So this thing calculated new Born virtual and integrated subtraction matrix elements. The real correction was still there from our previous fixed order example. Okay, now this is being matched to the okay, super. To the Catani-Seymour dipole shower. And we are generating events. Takes about a minute to generate these events. So maybe in the meantime, are there any questions?
Just a heads up that I'm going to have to leave in about 15 minutes for the next meeting.
Yeah, we will be done in 15 minutes. So this is really almost the end of the tutorial. So after this, we are going to do the merging, and then that's really it, basically. We're not going to go through NNLO because it takes too long. But after you've seen all of this, you've basically seen the basic use cases for Sherpa, and you can go from there. And if you have questions, you can always email me or any other Sherpa author to find out what's going on, or maybe not.
Let me take the minute to say thank you very much in advance, because this has been working really great. I'm really doing this in parallel, and it's working out nicely.
Okay, that's great to know. Thank you. Let's see. Oh, actually, while this is still running.
I will say your computer is doing something better than mine for this one. I'm running with 6 MPI threads, and it's a lot slower.
Okay. Yes, that is a very good point. Thanks for that comment. So at low multiplicity, MPI is actually not helping you. The reason for that is that the communication required between the different threads takes longer than the actual calculation.
Yes, okay, that makes sense.
And that's because we are communicating the information that is needed to optimize the integrator, which is essentially the entire Vegas grid. So for each channel, it's about 100 bins. And it's the bin positions, and actually we don't communicate the bin positions. We communicate the bin entries and uncertainties. And because there are quite a number of those, it takes a while, right? So you have to be at the crossover point where this is faster than actually calculating the matrix elements. Good point. And this is also why you don't expect scaling, right? And this is actually very important to understand where the limitations in scaling are on the big machines, even for the large processes, because you can imagine that if for, let's say, deep elastic scattering plus 5 or 6 jets, you go to the point where you have such a big machine, like, for example, Mira, that was an older machine at Argonne, or let's say Theta, the current machine, you allocate the entire machine with its 700,000 cores, and you are at the point where you only calculate a single phase space point on each core. You can never expect scaling because that single phase space point, even for a very complicated process, takes about a couple milliseconds, whereas the communication across the entire machine will be very much slower, right? So at some point it will flatten out and you have to find the optimum, basically. Okay, so hopefully I was smart enough to move the other file on time because I want to use it. Okay, that's good. Because I didn't do what I said in the slides. I didn't write it to a new file, and the default file name is always analysis.yoda. So let me write this now, move this now to a file that's called mcnlo.yoda. And now I already moved the old file, which is now called ps.yoda for Parton shower. So now let me do rivet make HTML, and I compare the Parton shower output to this mc@nlo output. Again, we'll take a second to plot this. All right, so now if we go back to our plots here, we will have an mc@nlo result in blue, which is slightly better than the Parton shower result in red. Okay, especially here for the transverse energy correlation. So now we can go from there and say, okay, if we want to make that even better, okay, first I should say, okay, I already said this before. If you want to learn more about how all of this works, you go to this resource. This is unfortunately a screenshot from the 2017 tutorial, but the tutorial itself hasn't changed, only how we run it, either using virtual machine or container. You can go to this resource, which I've shown before, and go through this in detail. Next thing I want to show in the last few minutes is the multi-jet merging. I believe this has been explained before. This works. Let me just briefly mention it again. So this is an example for PP to TD bar Higgs. So the example that I showed on the first slide. So time goes in this direction, basically. And what the Parton shower describes is really the inner jet structure. So it adds additional radiation by means of these blue dots here, which are supposed to be Parton shower emission kernels or evolution kernels. And you can do this for any number of partons, which is why there are the blue dots here, and they give you a good picture of the inner jet structure in the detector. So this is a simulation of mini black hole production in CMS, and I like it because it's so messy. Whereas you can also go the other way, you can say I do an exact calculation and I add additional partons to the hard matrix element, which is represented by this red blob here. And then you can ask yourself, okay, what's the overlap on the diagonals? How do I remove it? And this is done through multi-jet merging and of course also through matching, but I want to emphasize the merging here. And you can do this up to a certain maximum number of partons in the final state, which is where you run out of steam in your calculation. So this typically describes the kinematical distributions very well, much better than even fixed order calculations, because you can go to very high multiplicity. And in particular, in the context of EP simulations, this is very important because you have a lot of energy in the proton. And what you can do with this is to simulate, for example, BFKL-like effects explicitly by adding a fairly high number of partons in the final state, let's say 4 or 5. Okay. And when you do something like this is not DIS, unfortunately, that I'm showing here, but this is from PP. This is the diphoton azimuthal decorrelation in diphoton production. You can see here in comparison between a next to leading order calculation in gray and a merged simulation, matched and merged simulation from Sherpa. You find that the matched and merged simulation matches the data in pretty much the whole phase space, as opposed to the fixed order NNLO calculation. Also, the NNLO calculation has a very large uncertainty, because for the observable here, it's not actually an NNLO, it's just next to leading order. And there are just kinematic effects and partonic channels missing here that you catch with this merging procedure. So in other words, you get more physics in the red distribution than you get in the gray, and this is why it agrees much better with experimental data. And that's a statement that is almost universally true, except that in deep inelastic scattering you have to be very careful that you don't break the unitarity of the simulation. Okay, you can also do this with electroweak corrections, and here's an example from the LHC, where at high transverse momentum of the jet in vector boson plus jet production, you have a fairly large negative electroweak correction, which is a known effect, and you can include this in the merging. I don't want to go into details. You can also do on-the-fly uncertainty assessments for these merged simulations, and in newer versions of Sherpa, there will be on-the-fly merging scale variations. Let me just show you how it works. So we change the process declaration slightly. First, we add this additional jet with a curly bracket to the process declaration, which is this thing. Okay. And here you really specify the number of additional jets that you want. So if you don't want to run the tutorial by the real life example, you could just go to 3 or 4 here. Okay. But we want to have this in finite time, so we stick to 1. Then what we are doing is we add this curly bracket 2 to our MC at NLO, which means we want to stick to the NLO simulation for the inclusive process only. That is the 2 particle final state. So this 2 refers to these 2 particles. If you also want the NLO simulation for the 3 particle final state, you would add a comma 3 here. Okay, and then you could put additional particles at partons at leading order here by saying 3, for example. Same thing here, matrix element generator and magic also only for the 2 particle final state, and for this real emission generator comics here. Okay, now we are going to merge using the CKKW procedure, and we want to do merging only in QCD. So this is why we put a specific QCD order here. We don't want to have higher order electroweak corrections. And we specify a merging scale. This scale choice is explained in detail in a paper from 2009 by Thomas Germann, Tancredi Carli, and myself. And this has to do with the dynamics of the DIS process that I explained earlier on. This merging scale choice also smoothly interpolates, very much like this randomization factorization scale choice between these 2 different scenarios. Okay, and this is also given in the Sherpa example run cards for deep inelastic scattering. So you can just take this as a given for now. It looks a bit complicated, and if you want to understand what's being done by it, go to this original paper that is referenced in the Sherpa manual. Because we merge, we should remove this scale choice, because it will not be Q squared when you have a 3 particle final state. Sherpa will choose this automatically when you specify CKKW here. And it will always default to Q squared in the inclusive DIS process, but in the DIS plus 1 jet process, it will choose something different that's consistent with this merging procedure. Okay, and this is it. So we call this type of simulation MENLOPS because it's partially next to leading order because of this 2 here, and it's partially leading order because we have added an additional jet, which is only simulated at leading order accuracy. Okay. If you added a comma 3 here everywhere, in order to also have the 1 jet process at next to leading order, it would be a next to leading order merged simulation. Okay. And you can do this. I just didn't want to do it for the tutorial because it takes too much time. Okay, so let's do this. Sherpa will now calculate an additional cross-section because we have a process that is actually a 2 to 3 with an additional jet in the final state. it is similar to this process here, which also has an additional jet in the final state, but this time it's not a real correction for the NLO calculation, but it's actually an individual leading order process. Okay, so the calculation, so now Chopper performs the calculation for this particular leading order process. And okay, maybe in the interest of time, sorry, I only started this on a single core. Maybe that was a stupid decision. I'm just, in the interest of time, reducing the required Monte Carlo uncertainty here and let Chopper generate some events, which should be fairly quick. And in the meantime, take any questions that you may have. Are there any more questions at this point?
Because maybe while this is running, not directly to the matching and merging, but to what extent has Sherpa already been validated against DIS data, which would be mainly the Hera data?
So, right, let me answer this very much on the fly. So, if I can pull up Inspire, there is a paper by Tancredi, Thomas, and myself. Sorry, this one here. Which has the validation in great detail. So, as I said before, the scale choice that we are using at the moment and the dynamics of the process are explained here. This again explains this transition to the photo production region. So this is this merging scale choice here, okay, that I just plugged into the run card. And you really need this in deep elastic scattering in order to reflect the dynamics of the process. And then we have some validation here, and we have comparison to Hera data. And okay, it's all at the end of the paper. There are many interesting plots here. This is a particularly interesting observables where we check for the transverse energy of the jet in the bright frame divided by Q squared. So when this goes above 1, you are in the situation where you actually have QCD Compton scattering instead of a DIS process. And you see that when you only simulate with 2 additional partons, you're by far not matching the data. And this was puzzling people at the time when this analysis was performed quite a bit. But if you simulate with up to 5 additional partons, you're nearly spot on in all the rapidity regions. And of course, the forward region is usually the most challenging. You can do uncertainty assessments on that with Sherpa. So, and I should mention that all of these plots were made with HZTool. Okay, so this is with our dedicated HZTool interface, which I set up at that time. There are more uncertainties related to parton distribution functions and in PDF 1.2 at the time, and randomization factorization scale uncertainties, which are naturally larger in the forward region than they are in the central region. There are variations of shower schemes here, different recoil strategies, as we call it, variation of PDF sets. This is an interesting observable. It's the dijet cross-section as a function of Q squared and the combined ET cut on the different jets. That was an observable that prompted an analysis by Stefano Friccione, a very famous paper that is cited in our paper here, which really pointed out a numerical instability of the perturbative QCD calculation when you have symmetric cuts on the transverse energies of the jets. So you need an asymmetric cut, which is also being used in prompt photon production at the, prompt photon production at the LHC, dijet production at the LHC, and recently we have pointed out that this is also needed for even Drell-Yan measurements at the LHC. So it's a very well-known kinematic effect, which prompted this analysis. Before that, the Monte Carlos did not agree with data. Again, we can see here in the low Q-squared region, where you have this kind of inverted scale hierarchy, that a simulation with only 2 additional partons does not cut it. It's far off the data. This is why none of the Monte Carlos at the time that the analysis were performed matched the data. None of the D-club-based Monte Carlos, I should say. But even with the D-club-based Monte Carlo and with high enough multiplicity, in this case, you can match these data very well because you're explicitly simulating BFKL type of effects. Again, uncertainty estimates on this, PEF variations on this, shower scheme variations on this, jet ET spectra, jet rapidity spectra, cross-section as a function of x and q squared in different bins and as a function of this separation cut between the 2 jets, which is called delta in great detail. That's the x and rapidity, the delta rapidity spectrum. We have the 3-jet cross-section here and the 3/2 jet ratio, all measured at Hera in great detail. 3-jet angles, which were measured at Hera. Jet shapes, subjet shapes, transverse energy flow with 2 different fragmentation models. And then as a reminder, this is the difference between cluster and string. Okay, so assessed with the same shower, but with different fragmentation models in different bins of x and q squared. So this is basically, and transverse energy flow again, or PT spectra. So this is everything that was available and of interest in HZ-Tool at the time. You can have a look at this publication. So that's basically the validation that we have. Okay, so now we have the results. Logs.yoda. Let's plot them. And I would ask you to think about whether this simulation should or should not look different than the MCAT-NLO simulation that we performed previously, and you can shoot me an email after the tutorial about what you think, or what you thought, and why you think that it should or should not look different, and what you could do, also maybe based on what I just said about the simulations, to improve that. Okay, so sorry about that. We should be here. Okay, if you didn't guess, the simulation does not look different. You can think about why it doesn't look different. So we are comparing green to blue, or just speak up. Yeah, let me know why it doesn't look different, and think about what you could do to make it look better in comparison to experimental data. Of course, there's quite a bit of fragmentation dependence here on this particular observable, and I would also have to run cluster versus string fragmentation, but we are at the end of the tutorial, and unfortunately I figured yesterday that the interface to Pythia is not installed in the container, so you could maybe try to do this on your own. What you would need to do if the interface was installed is you would have to run Sherpa with the additional commands -f for fragmentation model, Lund, and -d for decay model, Lund. Okay? And then it would switch to Pythia fragmentation and decays. You could also put this in the run card. As I said, all the command line parameters can also be put in the run card. You could say here fragmentation Lund, decay model Lund. Okay, and that would give you string fragmentation. In that particular case, you would have to do the installation for Sherpa by saying configure -- enable Pythia. Okay, and whatever other parameters you had. Okay, and then you can try this out. Okay, and this is it. We are at the end of the tutorial. If you have more questions, let me know. Email any of the Shopper authors at any time about questions that you may have. And thanks for attending.
Thank you so much for the Shopper tutorial, Stefan. This was really great.
Thank you, Stefan. Bye-bye now. I have to go. Bye.
Okay, thanks.
Thank you. Bye.
Okay, then I stop the recording.